a mathematical model of a control system or the system is, we are going to discuss it. So first we are taking a mechanical translational system. So you know that the mechanical translational is the moving in a straight direction. Okay, so there are three main components which is present in the mechanical translational system. So one is a B, which is called as a dashboard, M, which is a mass, and K, which is a spring. So the dashboard, mass, and spring is the three main components which is present in the all the mechanical system. Okay, so this we are having the physical equation which will describe the equation of the each element. Okay, so the spring or dashboard will be described by, which is B into dx by dt. So it is a translational system, means an object moving in the direction of x or y. Okay, so it is described with help of the movement of the system with respect to the translational, which is in a linear movement. Okay, so if you take the displacement is x, we can take b into dx by dt, and the mass is represented by, so fb. So it is a fb and fm. Fm is m into d square x by dt square, and the k, fk equal to k into x. Okay, so this is the equation which will describe the function of the dashboard, mass, and spring. So which is described by b, and m, mass is m, and spring is k. So in a mechanical system, we can convert this dashboard, mass, and spring into this equation to derive the final output of what is the displacement arrived from the mechanical system, the combination of these three elements. Okay, so we can consider the example. So the dashboard is, it is drawn like this. So this is a B, and where you are providing the displacement of x is provided here. Okay, and the force. So the force is a Fb, and which is b into dx by dt. And for the mass, so we are representing the mass in the rectangular block diagram with the m. Okay, so the m, we can have the m into acceleration. You know that the force which is falling onto the mass is, it is d square, so it is m into d square x by dt square. Okay, so it is like that, f equal to m into a. Okay, so it is an acceleration and spring. Okay, the spring is, it is represented like a helical coil. Okay, so it is represented by k, and the displacement of this one is x, and again the displacement of this one is x. Okay, and this is the input force F. The input force is given is F. So the F which is in a spring, it is called as a Fk. F in a that is, F is nothing but a force. Okay, in a linear motion uh, we are calling it as a force. If it is a rotary motion, we are calling the force as a torque. Okay, so the force for a spring, dashboard, mass, and spring, this is the equation, and this is the symbol represent these three basic components. Okay, so now we are going to derive a mathematical equation for a simple mechanical system. Okay, Okay, so here the one side it will be connected with the reference, and another side is the force is given. Then this is the equation. If the two side we are having there is a no connection, or the element is connected in common between the two elements, so we can discuss the derivation. So before that, if the element is connected between the two elements like that, it is not connected in reference means, okay, um, it is a B. So here it is connected with the displacement x1. Here the displacement x2 is connected. So the final equation which will describe this one is Fp equal to B into d of x1 minus x2 divided by dt. So in the same way, if the mass is connected common between the 2 points or two displacements, here it is x1 and here it is x2, then we can write the equation as Fm equal to m into d square by dt square of x1 minus x2. And the same way, the spring, if it is connected between the displacement of x1 and x2, then Fk equal to k into x1 minus x2. Okay, so this is the way you can write the equation for all the mechanical elements. Okay, so this is for uh, with the reference, and this is the common between the 2 points or two nodes, we can call it as. Okay, here in a mechanical system we are making all the masses as nodes. Okay, so we are going to derive the mathematical equation for this mechanical system. Okay, so the problem we are going to the first problem we are going to derive it. So first we have to write the free body diagram for the mass 1, then we are going to derive the free body diagram for mass 2. Okay, so the first mass 1 is free body diagram, so we are going to write the free body diagram for mass 1. So this is a basic equation. Okay, we'll have it in the board. So first one is solution is free body diagram of mass m1. Okay, so we are writing the free body diagram. Okay, the mechanical system m1, and the displacement of this one is, it is a y1, and so here you have to represent the force also, f of t, f, and we are writing it as the input force is, displacement of this object is 1 and input force is f, and the force. Okay, so we have to write it in the opposite direction. First, the input force is given in the outward direction, and the other opposite forces in the opposite direction. So always we are representing whether the force may be incoming force or outgoing force. So we are, while you are writing the equations, so the force will be in a one direction, the other opposing forces from the elements should be in a opposite direction. Okay, so this Fk, here you have to write the force due to the mass is connected between K1, B and K2. So we have to write the equation for all these things. So we have to write Fk1 and d to the B, so it is Fb, and K2, so it is Fk2, and d to the mass Fm. Okay, so these are all the forces. So we have to write the force balance equation for this system. Okay, so the force balance equation we can write it from this, the basic equation. So for, if you write the force balance equation, so F K1 plus Fk2 plus Fb plus Fm equal to F. Okay, so the sum of incoming force equal to sum of the opposing forces. Okay, so you will get equal to F. So what is Fk1? So you know that Fk is k into x. So Here you see that the k is connected with the reference, so we have to write this equation fk. So we have to write k into, so here what is the displacement? It is not x, it is a y1. So we have to write k into y1 plus fk2. So the k2 is connected between m1 and m2. So we have to write this equation. So k into y1 minus y2 plus fb. So here fb is connected, one point is connected to the reference, another point you are having the force. So you have to write this equation b into dx by dt. Okay, so b into dx, here instead of x you have to write y1 by dt. Okay, plus fm. Fm is, so here m is connected between the reference to the first point. So we can write this equation m into d square by dt square into y1. Okay, so here the displacement is y1, here it is y2, which is equal to f. Okay, so we can write the Laplace transform to convert this the mechanical equation into in a S domain equation. Here before that we can rearrange the equation. So m into d square y1 by dt square plus b into dy1 by dt plus k into y1 plus k into y1 minus y2 equal to f. Okay, so first mass, damper and spring we are writing, because while you're converting into the Laplace domain, here the second order differential will be in a s power, and first order differential will be in a s, and it is in a uh, normal coefficient. Okay, so if you take the Laplace transform of equation 1, so if you take the 1, then we are going to take the Laplace transform of 1. Okay, so if you take the Laplace transform, then you'll get m into, so the d square second order term will be s square into y1 of s plus b into the first order differential is s into y1 of s plus k into y1 of s plus, that is k1, actually k1, this is k1 and this is k2. Okay, k1 and k2 y1 of s minus y2 of s equal to f of s. Okay, so we are getting this uh, mechanical equation. So this is the final equation for the mass 1. Okay, so again we will go for, so you can take the y1 and y2 commonly, then we can get the simplified equation. So if we write m into s square plus b into s plus k1 plus k2 into y1 of s minus k2 into y2 of s equal to f of s. So this is the mathematical equation for the first mass, and I'm going to derive the mathematical equation for the second mass with respect to the second mass. Okay, so we are going to write the free body diagram. Okay, so the next one is we are going to write the free body diagram for mass m2. Okay, so the free body diagram for mass m2, the same what how you derived for the mass m1, in the same way we are going to derive it for the mass m2. Okay, this is a mass m2 and the displacement at this mass is y2. Okay, so what are the incoming forces? There is a no incoming force, so all are opposing forces. So what are the force acting on this one is it is d to the spring k2 from the here m2, we are having the spring k2 on only the mass. Okay, so it is a force d to the mass. So these are all the two forces acting on this mass. So if you write the force balance equation, we are getting fk2 plus fm equal to, there is a no force, so the equal to 0. So if you substitute the fk2 and fm, so fk2 is, the k2 is connected between m1 and m2. So we have to write for the spring, we have to write fk2 is k2 into y2 minus y1 plus fm, we have to write m into d square y2 by dt square equal to 0. Okay, so again in the same way we are going to write the take the Laplace transform. If you take the Laplace transform, so we will get k2 into y2 of s minus y1 of s plus m into s square into y2 of s equal to 0. Okay, so we can write the derive the y1 in terms of y2. Okay, so if you take the y2 outside, y2 of s into k2 plus m into s square, okay, and minus y1 of s into k2 equal to 0. So if you rearrange the equation, we will get y1 of s equal to, it will go to that side, 1 by k2 into m into s square plus k2. Okay, so if it is go to the right hand side equal to k2, then it will come into the denominator, so you will get this equation. So we are going to substitute this equation 2 in a equation 1. So I'm going to substitute, so this is, if you take this is 2 and this is 3, you will get, so you have to substitute equation 3 into equation 2. Okay, if you substitute, we will get m into s square plus b into s plus k1 plus k2 into the y1 is 1 divided by k2 into ms square plus k2. Okay, minus k2 into y2 of s equal to f of s. Okay, so again by rearranging the equation or taking the y of s commonly outside, so here you have to write y2 of s. Okay, so if you take the y2 of s commonly outside, we will get y2 of s equal to ms square plus bs plus k1 k2 into ms square plus k2 divided by k2 minus k2 equal to f of s. Okay, so if you rearrange the equation, that is a transfer function is the Laplace transform of output to the Laplace transform of input. Okay, so the Laplace transform of output is, here it is displacement y2 and input is your f. Okay, so we have to derive y2 divided by f. So if you take this, we'll get, so the transfer function, I will write it here, transfer function equal to Laplace of output divided by Laplace of input. So the output is, here it is y2 of s divided by f of s. Okay, so it will come into the denominator. So this equation will go to k2 divided by, if you take the LCM here, you will get ms square plus bs plus k1 plus k2 into ms square plus k2 minus k2 square. Okay, so this is the mathematical equation which will describe the mechanical system which is shown in the figure. So in the same way, we are going to derive the mathematical equation for any type of mechanical system which is a combination of the mass, damper and spring. So in the same way, we can also derive the mechanical equation. So we can derive the equation for the rotational system, okay, where the displacement is represented with help of theta. Okay, so we can convert this mechanical equation into the equivalent, the electrical system. Okay, how we are going to convert this mechanical system into the electrical system is by using the mechanical to electrical system conversion. Okay, that is called as a force voltage analogy. Okay, so we are going to derive the force voltage analogy for the same example what we derived now. Okay, so first we will discuss about what is meant by force